Hello, hi, welcome back to CS700, Computer Science of Continuous Data, Algorithmic Foundations of Numerics. Let me show you the slides to recall what we have talked about in our last lecture. So, in our last lecture, we talked about notions and properties for computing a real function. And our first notion was based on the conception that a function is a transformation, a continuous dynamic object that receives, in this case, a real number as argument and produces a real number as value. And real number values, we already have a definition for that, namely outputting an infinite sequence of rational approximations, more precisely integer numerators of dyadic approximations up to error bound 2 to the minus n, and extending that from mere output of a single real number value to transformation of a real function means to have both such a sequence of dyadic rational approximations for input and for output. And this was our first definition. And with this gives rise to some interesting properties. Closure under restriction, closure under composition, all the nice properties, but also maybe not so nice property, namely that any computable function is necessarily continuous, basically because of this infinite sequence of input approximations where within finite time, any reasonable algorithm can have seen only a finite initial part of that infinite input sequence. And we've seen some equivalent alternative characterizations of computable real functions, among them the computable version of the classical Weierstrass theorem, namely, since any computable function must be continuous anyway, we can consider functions which can be approximated uniformly by polynomials. And according to Weierstrass, every continuous function or compact domain can admit such uniform approximation by polynomial sequence. And the computable version says that this is also true for a computable sequence of polynomials with, let's say, dyadic rational coefficients. And this gave rise to our second characterization where a function is considered as a static object, namely something that kind of lives in the Cartesian product space of domain and codomain and is to be approximated by a sequence from a dense countable subset. In the case of real numbers, our dense countable subset are the dyadic rationals, and in the case of the Weierstrass theorem, our dense countable subset is the set of all Weierstrass polynomials with dyadic rational coefficients, which you can easily see to be indeed dense and countable. And the computable version says that computable functions as transformations are precisely those which can be uniformly approximated with error 2 to the minus n by computable sequences of such Weierstrass polynomials. And for our third equivalent characterization, we had to introduce a quantitative version of continuity of uniform continuity, namely a modulus, which can be regarded as a scolomization of the epsilon delta conception of continuity of a function. Namely, a modulus is a mapping from natural numbers to natural numbers and thus pertains to the classical discrete notion of computability. And the third notion and definition of computable real function, again, makes use of the property that we're talking about only about continuous functions. and continuous functions are already uniquely defined by their values on a dense sequence of the domain. So, and here we consider special dense sequence in the domain, namely this sequence of all dyadic rationals that belong to the domain 0-1 interval. And since this is a countable set, we can order it arbitrarily, let's say lexicographically, and then this gives rise the values of the real function on that sequence give rise to a real sequence. And the third requirement says that this must be a computable sequence in the sense that we've talked about before. And the second requirement is that the function must not just be qualitatively continuous, but quantitatively, computably continuous in the sense of having a computable modulus of continuity. And then the theorem says this third definition is again equivalent to the former two. And this is generally and generically strong evidence for a definition to be reasonable when there are two, or in this case even three, superficially unrelated definitions, reasonable definitions that then turn out and are proven to be actually equivalent. And we didn't really prove the three equivalences between, or equivalence between the three notions. Some of the proofs are easy. For example, that B implies A. That is pretty immediate, and I want to leave that to you. Also that C implies A is rather obvious, and actually that's part of our simplified proof strategy. Proof that C implies A, and then proof that I implies C. That's actually pretty subtle. The first part is obvious, that the values on dyadic rationals are computable sequence. That follows immediately from the definition, but that any function which is computable in the sense of a transformation must have a computable modulus of continuity. This is something we're going to prove at the end, hopefully, of today's lecture. And the equivalence to B, between B and C, that's basically having again a look at the classical Weierstrass theorem and its proof, which turns out to be a constructive proof. First, you approximate the absolute value function by polynomials. They are explicit polynomials that approximate the absolute value function, let's say in the interval from -1 to 1, right? You can imagine that absolute value function and polynomials that approximate that uniformly. And then you combine these polynomials, or actually the absolute value function, in order to create piecewise linear functions. Okay, and with piecewise linear functions and a modulus of continuity, you can then approximate any other uniformly continuous function. And we'll see how to approximate any other uniformly continuous function given a modulus of continuity in 2 slides later, when we talk about computability of Riemann integral and of maximization. So please stay tuned for that after we've finished the recap. So then we've talked about modulus of continuity and how that quantitative notion of continuity recovers some of the quantitative notions that you probably have learned about in calculus, namely Lipschitz continuity and Hölder continuity. And we've seen examples of functions which are not even Hölder continuous, and which have not even no polynomial modulus of continuity, but an exponential one. And then we've seen an entire hierarchy of such functions whose modulus of continuity necessarily climbs up a tower, a sequence of towers, exponential towers in modulus of continuity. Right, and finally we discussed some examples of computable functions the arithmetic operations are computable. Also, the square root as an algebraic operation is computable, and so some of the important transcendental functions like exponential function, natural logarithm, trigonometric functions are computable on their natural maximal domains. For instance, the logarithm on the domain from 0 to infinity, excluding 0, of course. And I'm going to recall the proof in a minute of some of these examples. We've also seen that some important operators map computable functions to computable functions. We have not talked about computability of operators, mind you. This is going to be a separate chapter in this course. But we can say already, since we know what it means for a function to be computable, that the indefinite Riemann integration operator maps computable function to computable function, which is a similar way of saying that computable functions map computable real numbers to computable real numbers, which is true, but which is not equivalent to being for function to be computable. It's only a necessary condition, but no sufficient. So, here's for your convenience some graphic that demonstrates the meaning of this parameterized maximization operator. So the Riemann integration operator, that's what you're familiar with. So argument is a continuous function, and value is its antiderivative. So the integral from 0 to a given parameter x. So that this is again, the value of this operator is again a function. This is not a functional. Definite Riemann integration would be a functional, but indefinite Riemann integration is an operator whose value is a function. And similarly here, the maximum is also an operator. Argument is a function, and the value is a function. Namely, take the maximum of the given function up to the given argument x. And the result is a non-decreasing function that is depicted here in red. So black in this example is the function f, and red is the maximum of f as a function of our argument x, like here. We also talked about another operator, namely the join operator, that kind of glues together two functions. Let's call this function f and g. The first function is defined on the negative unit interval from -1 to 0, and the second function is defined on the positive unit interval from 0 to 1. And here you can see two such examples, and the hypothesis of the statement is that both functions are computable, and the claim says that then their join is computable, gluing them together at the joint point of their domains at 0. Now, this obviously cannot be true, right? Because you see in this example that gluing together these two functions will result in a discontinuous function. There's a gap here and jump, and we know very well that discontinuous functions are not computable. So the way the statement is presented here is obviously wrong. So let's correct that by adding another hypothesis, namely the hypothesis that the two computable functions agree on the join point of their domains, maybe at 0. Okay, so this is wrong. And now it's true because these two functions are not only computable, but also agree at 0. And we're going to see a proof in a minute on the next slide, so stay tuned for that while we finish the recap. And finally, we stated without proof that the so-called modifier, which you may or may not know from advanced calculus or from functional analysis, is computable. Modifier is a smooth function, a C infinity function, continuously differentiable infinitely often, yet it vanishes outside of the unit interval from -1 to +1. And this is something pretty peculiar because, for instance, for analytic functions, functions that can be expanded into a power series, this cannot be true. Any analytic function that vanishes on a set that includes accumulation point must necessarily be identically zero. That's a uniqueness theorem for analytic function. So this modifier is often used as an example of a function which is infinitely often differential, yet cannot be expanded into a power series. It's not an analytic function because expanding it into a Taylor series, let's say at point +1, would result in the zero function because its function and also its derivatives vanish at zero. And here you see a picture of this function. And the statement says here that this is a computable function, and we will use that in the sequel frequently to construct counterexamples. So we use positive examples, namely the computability of this modifier, to construct uncomputable functions counterexamples. Okay, and let's sketch some proofs of computability of the aforementioned functions and operators. First, let's recall the exponential function from the real numbers, entire interval, real numbers to the real numbers. And the statement is that this is a computable function, and now we exploit that we have three different but equivalent notions for a function to be computable, and we just are now free to pick whichever of the three notions we find most convenient. And here maybe it's the definition that says, according to computable Weierstrass theorem, namely approximate that function by a polynomial uniformly. And here you see such a polynomial, namely just take the standard power Taylor series expansion of the exponential function that you're probably well aware of, and take the first n terms, and then it's a matter of classical calculus and tail estimates to see that omitting all the terms of order n+1, n+2, and so on gives rise to an absolute error of optimal at most 1/2 to the n, provided that the argument t is in the range from -1 to +1. So here you can see a picture. Red is the true exponential function plotted from -infinity to +infinity, and of course it tends to 0 for -infinity. And you can see the first 5 Taylor polynomial approximations. Green is the linear, blue is the quadratic, orange is the cubic, and then there's an order 5th approximation. And you can see that indeed in the interval from 0 to 1, these are extremely good approximations, but beyond that interval, the approximations are bad, and they don't really seem to get much better, as you can see. So this proof sketch of computability of the exponential function refers to this definition of what it means to compute a real function on a compact domain, on a compact interval k, namely approximated by a sequence of polynomials uniformly up to error 2 to the -n, where the polynomials, that means their degrees and their coefficientless, right? So every polynomial has a finite degree and finitely many coefficients that are here supposed to be the integrational numbers. So in this sense, outputting one polynomial in that sequence is something that takes only finite time. But if we have a sequence of polynomials, then not only the sequence of their coefficients, but also the sequence of their degrees is required to be computable. But here, this is indeed easy to see. Remember that the coefficients are basically 1/n factorial, which remember was one of the examples of a computable sequence, which we discussed. And the degrees are just n, right? So the degree of the nth polynomial approximating polynomial is n. So this is a very good sequence of approximations, but only on the unit interval, right? From from -1 to +1. So how can we prove that the exponential function is computable on the entire real axis? And to this end, we're going to use, like people in numerics usually do, the classical additive multiplicative property of the exponential function. And if we have an argument that lies outside the unit interval, maybe beyond positive real numbers, then we can apply an argument reduction. Namely, if we consider, for instance, the argument t plus k, where t is between -1 and +1, and k is some natural number, then the value is just the exponential function at t, which now satisfies the hypothesis, times a finite, namely k times multiplication by the Euler's constant, which is computable because we satisfy the hypothesis, the argument 1. And so this is finitely many multiplications. And now recall that we've already stated, although frankly not proven, that the set of computable real numbers is closed under multiplication. That product of two and thus of finitely many computable functions is again computable. This thus establishes that the exponential function is indeed computable on the entire positive real axis, and you similarly can deduce that it is also computable on the negative real axis. But here now we use a different definition of what it means to compute a real function. Our definition here from the computable Weierstrass polynomial does not apply, because this only applies to real functions with compact domains, and this is certainly not a compact domain. In fact, here we use a different notion of computability of a function, namely the one of mapping computable sequence to computable sequence. This is also the notion that we may, for instance, use to show that indefinite Riemann integration maps computable functions to computable arguments. Here, for your convenience, you can see standard example of the typical Riemann sums, right? Approximate the function by piecewise constant functions, and then add the areas of all these piecewise constant parts. And this gives an approximation, according to Riemann's theorem, to the integral of the original continuous function. But the important question now here is, how small should we make the segments of this piecewise constant approximation in order to arrive at final error bound 2 to the minus n, right? And this is where our modulus of continuity again comes to help. Namely, so here you see the width of these individual segments, and the statement says, let's make this width have error bound 2 to the minus mu of n plus 1, where mu is a modulus of continuity of the original function. And according to the third definition of what it means to compute a real function, such a modulus exists that is computable. It is, for instance, computable by a Turing machine or by a regular while program. And so we take that modulus to determine how small the width of the interval of the small intervals are. And then by the very definition of the modulus, that means that the value of the function in each interval varies by no more than 2 to the minus n plus 1. So that when integrating, taking the area of all these segments and adding, the total error will be indeed no more than 2 to the minus n plus 1. An additional error of 2 to the minus n plus 1 comes since we can only approximately evaluate the given function on each of these piecewise constant parts. So if we approximate the function, evaluate the function approximately up to error 2 to the minus mu of n plus 1, up to error 2 to the minus n plus 1, then adding both errors, the tail error from taking finite uh, Riemann sums, and the error from approximating all the function value together add up to yield a guaranteed error bound of 2 to the minus n for the Riemann integral. Okay, so that's concludes the proof sketch of the second operator to map computable functions to computable functions. And I leave it to you to slightly modify that proof to show that also the maximal operator maps computable functions to computable functions. Again, hint, hint, use the property with having a computable modulus of continuity from the third definition of what it means to compute a real function. And finally, how about this join operation, right? Remember the join operation and classical argument might try to prove the join of these two functions computable by checking whether a given argument is greater 0 or smaller than 0. But that's the naive approach does not work in case that the argument is equal to 0, because then the test, the comparison does not return at all. Remember that test for equality is undecidable. Instead, we could, for instance, use this definition that function to be computable and must map a sequence of diagonal arguments to computable sequence, and that indeed applies to the to 0 as well. 0 is diagonal arguments, and applying the second part of this definition about the modulus of continuity. If we have a modulus of continuity mu of f and another modulus of continuity, let's call it nu of g, then the maximum of both moduli of continuity, the maximum pointwise maximum of mu and nu, is easily verified to be a modulus of continuity of the join of the two functions, and thus also we get that the join operator makes computable functions by conveniently using the third definition here. You can also prove it using the other two definitions. Of course, they're equivalent, but the proof is less elegant, so I've deliberately chosen this definition in order to arrive at an elegant proof. Okay, so this is kind of a recap of computability of real functions, and now we start with something more advanced, namely advanced aspects of computability of real functions involving negative statements, counterexamples that seem maybe surprising. This is one of the strengths of science, that we can prove something is fundamentally impossible, and indeed that gives good guidance to what we can expect in numerical computing. So we're going to recall some results, for instance, from Myhill, 1971. Right, Myhill, I think you met as computer scientists might know him from the Myhill-Nirodi characterization of regular languages. Does anybody remember that? A language is regular if and only if it has consists of finitely many equivalence classes. Anyway, okay, if you don't know this, then it's pointless. And if you do know it, then please remind yourself. That's the same Myhill from the Myhill-Nirodi theorem, and in 1971 he proved that the derivative of continuously differentiable functions is an operator which maps computable to, in general, uncomputable functions. 1979 is about ordinary differential equations, computable ordinary differential equation, where the solution, all solutions actually are not computable. That's Puel and Richards. Then we're going to recall also uncomputability with partial differential equations, namely the wave equation and partial differential equation, which we're going to show, following Borel and Richards 1981, to map computable initial condition to an uncomputable initial condition. So these two are used to demonstrate that class solving differential and partial differential equations numerically may be much more subtle than one can expect, and standard approaches of like discretizing the data to solve the differential or ordinary differential equation on the discretization on a grid may, well, in general, of course, it will happily produce some output, but this output may not in general be related to the actual mathematical correct solution, right? And there's no warning. If you feed the wave equation to your favorite system, then it will happily produce figures, pictures, graphs. But the statement of Borel and Richards 1981 says that this will not, cannot be approximation up to arbitrary error to the actual solution in general. Similar, the argmin function, the operator that functional that returns argument where the function attains its minimum, a given continuously differentiable, or in this case even a smooth function, or returning a root of such a function, is in general uncomputable, and thus whatever promise your favorite library may make, it must be lying when it says it can do this, and smoothness does not help. We're going to recall this counterexample, this construction. And finally, this construction will be based on so-called singular coverings, that is covering all computable real numbers by small open sets. Recall that there can be only countably many computable real numbers. So by putting small open intervals around each computable real number and making the intervals small enough, one can actually put all computable real numbers into an open set which has arbitrarily small measure. In our case, we will make it have measure 1/2. And the interesting thing is that this open set will turn out to be computable. Finally, we'll recall what we talked about, quantitative continuity, and we will prove finally this important part of the computable Weierstrass theorem, that any computable function is not only necessarily continuous, but must have a computable modulus of continuity. And that's here really compactness enters crucially of the domain, right? Any computable function, a compact domain, is uniformly continuous, and modulus of continuity captures uniform continuity, and we're going to do that in a computable fashion. So that's our plan for today's lecture. And we start with the Myhill example. We're going to construct a function which is computable and continuously differentiable, that is of class C1, so that its derivative is not computable. Okay, let me say that again. A function which is continuously differentiable and computable, but its derivative, which exists and is continuous by hypothesis, but its derivative is not computable. Okay, and the sum point is that the function we're going to construct is going to be computable in the sense like it can be approximated by Weierstrass polynomials, but we're not going to approximate its derivative. And that's the whole point, right? If we could approximate its derivative, then taking the derivative would give an algorithm for computing the derivative, right? But the function we're going to construct will deliberately be constructed such that only the values of the function can be approximated computably, but not the values of its derivative. And for this purpose, we're actually going to construct the derivative first, and then consider its antiderivative according to the parameterized Riemann integral. So our constructive proof proceeds the other way around. We first construct the uncomputable function, and then we integrate that uncomputable function to obtain a continuously differentiable function according to the main theorem of calculus, and in such a way that this antiderivative, this integral, that this be computable. So that's our goal here. And in order to see the construction, we start with this head function, right? This is a function that has support between 1/2 and 1. This half part of the unit interval, it's just like Lipschitz continuous function, but it vanishes outside here. We're going to put scaled versions of that function into other subintervals of smaller and smaller scale, both in x and in y direction, while maintaining the Lipschitz continuity. So here you see the next head function. It's half the size in x and in y direction. Here it's 1/8 the size, and so on. And observe that both this function, this head function, is computable, and its integral is computable. And when we scale the head function, here you see the scaling. Here it's the scaling in y direction, and here you see the scaling and shifting in x direction, right? So this is scaling and this is shifting in x direction, and both simultaneously. This makes the area under the function, the Riemann integral of the function, scale with 4 to the n or with 2 to the 2 to the n, right? Because we scale both x and y. So reducing both height and width by a factor of 2 reduces the area by a factor of 4. And this is exactly what is recorded here for later convenience. And so if we scale both x and y direction, the resulting function, the resulting heads will still have the same Lipschitz constant as the original ones, right? So for instance, this function is constructed to be what, like 1 Lipschitz or 2 Lipschitz, anyway, some constant Lipschitz. And these all have the same Lipschitz constant. And this allows us to put all these functions together into a formal sum, infinitely many functions on this infinitely decreasing sequence of subintervals. And since the function sequence decays in width and height, that means that they tend to 0. So that this infinity function join, right? This is a join of functions. This infinite join is again continuous, including continuity at 0. So this is a continuous function. Also observe that convergence is not an issue here, although it's an infinite sequence series sum of functions, but they have disjoint support. So wherever one function is non-negative, all other functions are 0 anyway. So that this is only a formal infinite sum for any single point. The function, this sum is actually trivial, has only one non-zero term at most. And this resulting function is computable, right? We've been careful enough to make sure that when we glue these individual heads together, they have agreeing value. And the only difficult point here is at 0. But since the function sequence converges to 0 with height 2 to the minus n, that means we can easily also compute the function. Namely, given a real argument, we can check whether the argument is sufficiently large, has argument larger than 2 to the minus n, and if so, then we pick the corresponding head here in the sequence. And if the argument is less than 2 to the n, we're not going to test whether it's 0 or not, because that would be undecidable. Instead, we simply output 0, because for arguments that are so close to 0, it doesn't really matter what the exact value is. The value of the function will be also close to 0, because the resulting function is 1 Lipschitz. Okay, good. So far, so good. But now we're going to spice things up a little bit by throwing in the halting problem. If we do want to construct something uncomputable after all. And to this end, we're going to remove some of these heads here from our series. We're going to let the series index n run only over all n that belong to the halting problem h, right here. So that means some of these heads are now absent, are replaced by constant 0 function here. And that gives rise to a function which is still continuous, right? No problem here. Anywhere here, no problem at 0, no problem. But the resulting function now is uncomputable. Why is this uncomputable? Intuitively, because we have thrown in the halting problem, but more formally, because we could solve the halting problem if this function were computable. Maybe we could, if this function were computable, then we could evaluate it at some midpoint, at any given midpoint of these small and smaller intervals, right? And if that evaluation turns out results in a value which is non-zero, and remember that being non-zero is semi-decidable, then that means that the resulting head is actually present and therefore belongs to the halting problem. That's not the interesting case. The interesting case is if the midpoint value is less than 2 to the n, right? Then it must be 0, right? So we don't even need to test for equality for 0. We only need to test whether the value of the function at one of these purported head peaks is less than 2 to the n. If it is less than 2 to the n, then it means that the head is absent entirely, and therefore that there's a constant 0 function, and therefore that this is an argument n which does not belong to h. And thus we can actually decide the halting problem under the hypothesis that this function is computable, which is of course a contradiction. This function cannot be computable. Okay, so we've achieved half our goal, namely an uncomputable function, by encoding the discrete halting problem into a continuous, continuous function. But our goal is to have this function constructed in such a way that its antiderivative is computable, right? And this is not the case for this construction, so we need to make this construction a little bit even further delicate and careful. And to this end, we replace the sum of all terminating programs, right? This n, every n here is a encoding of a terminating program with a given terminating input, and the sum is ranging over all such terminating programs, but this sum is of course, the sum range of the indices is of course undecidable. But then recall that the halting problem is semi-decidable, and one of the equivalent notions of semi-decidable means that it is enumerable. So that means there exists a computable bijection, let's call this psi, from the natural numbers onto the halting problem h, right? We talked about this when we talked about discrete computability. And now we're going to change the order summation here in the sum and replace n with psi of k according to this bijection, right? So this means reordering the sum. And this is what happens here, right? Instead of n, let me show you again, we replace n with psi of k. Here you see, right? So now we've changed the index and the order of summation here. And this function is now still continuous and it's still uncomputable. It's the same function as previously, now only with the order summation differently. Nothing has changed so far. And now we make a second amendment, second modification, namely we make the heads thinner. The height remains the same, but they become thinner depending on the parameter k, not depending on n, which is equal to psi of k, but depending on k. Or put differently, if in this enumeration of all terminating programs, if it takes long for n to appear here, if n appears only for very large psi k, if n is psi of k for very large k, then the head will still have the same height, but be much thinner. So this is what happens here. So we introduce this factor 2 to the k to make the heads thinner, while keeping all the scaling of their height. And now k indicates when this head occurs in this enumeration, right? So previously, this gives n is 1, n is 2, n is 3, and so on. But now n occur not in increasing order. This bidirectional is not necessarily decreasing or increasing or anything. So when a head occurs late in this enumeration, it will have a very thin, will be very thin. So this function is still continuous, right? So the height of the head tends to 0 as previously, and it's still uncomputable because, well, basically at the interval midpoints, the values have not changed, right? The values at the interval midpoints, which allow us to recover the solution to the discrete halting problem, have not changed. But now let's have a look at the integral of this uncomputable and continuous function. The integral, the indefinite Riemann integral, is computable. And that's the last statement of this slide that will conclude our proof, namely, once we've seen that this is computable, that will be our counterexample function, a computable, continuously differentiable function, right? Because it's the Riemann integral according to the main theorem of calculus, whose derivative, which we constructed to begin with, is continuous. So the function here is C1 function, but uncomputable. So put differently, this is an example of a continuously differentiable computable function whose derivative is not computable. Okay, so we're almost there. Let us observe why it is true that this Riemann integral of this function is computable. And the reason is that we've made these heads thinner, and therefore they contribute much less to the overall integral, right here. We've scaled their contribution to the integral with 2 to the minus k, if k is very large, or put differently, in order to approximate the integral of this carefully constructed, you can call it artificial function, fair enough, but in such a way that we only, in order to approximate the integral, we only need to look at the first k possible terms of this enumeration, because any later term, if n occurs later, then its contribution to the integral will be negligible. It will be smaller than 2 to the minus k, and therefore, in order to approximate the integral, we can simply omit that part. Whereas for the value, for evaluating the function, not its integral, but for computing the original function, the height is relevant, and that has not changed. Or put differently, we can also consider this as a exploiting the well-known fact that a differentiation operator is a discontinuous operator with respect to the supremum norm. That's the abstract perspective from function analysis. You know that, right? You know that differentiation is a discontinuous operation with respect to the supremum norm. And the supremum norm is really what matters here for the computation of the function. whereas for the computation of the integral, yeah, it's the L1 norm that matters. That's an abstract perspective of this construction. So to summarize, differentiation or even of a smooth function of continuously differentiable functions can map computable functions to uncomputable functions. So in future and in this lecture, the sequel of this lecture, whenever we see a derivative, let's be very careful and double check whether really the derivative of the function under consideration is computable, and not because in general it may not be. In the same way that whenever we have a limit, we must be very careful, because we have seen from Specker's example that limits, even of convergence sequences, can be uncomputable real numbers. Okay, so that concludes our first counterexample. And now we're going to proceed from here to the second counterexample that is actually based on this counterexample, namely the uncomputable wave equation. So what again is the wave equation? The wave equation is this second order linear partial differential equation. So it's second order in time, and this is a second order in space. So this is a Laplace operator, partial derivative with respect to x twice, plus partial derivative with respect to y twice, and so on for all possible spatial variables. Actually, it suffices if we have only two spatial variables here. And we need two initial conditions. First, we need an initial condition for the function value initially, and for its first temporal derivative as well. So we have two initial conditions, f and g. So this is a classical linear partial differential equation. Has been thoroughly investigated, right? This is what Maxwell equations are examples. Many examples, wave equation. This is what gave rise to the entire Fourier theory in classical calculus. And it seems quite surprising that this should indeed map computable initial conditions to uncomputable ones. But this is exactly what can happen. And to demonstrate that, I'm going to recall and refer you to Kirchhoff's formula, which gives a kind of explicit expression for that solution. So the solution at time t and spatial variable x vector can be written as the partial derivative with respect to time of this complicated expression. Observe that this is a surface integral, right? It's the over the unit, the circle or sphere with radius t, and center x, and y, that's what y ranges over. So this is the surface, y ranges over the surface of a sphere centered at x with radius t. And we take the average of the initial condition f on that sphere, shifted and scaled sphere. And yeah, this is basically just means taking the average, right? And then taking the derivative. And similarly, there's an expression that involves the other initial condition, namely the first derivative, which is also kind of a surface integral, but now without this partial derivative. And so the Purell and Richards observed that from this, it follows that there are computable initial conditions, f and g, for which the solution u of t and x is not a computable function, not a computable real number. And their counterexample actually doesn't even need this initial condition for the first derivative. And so what it does need is what we've just proved, namely the Myhill example of a computable continuously differentiable function of one argument, right? So here we have only one argument, and here we have actually one temporal and d spatial arguments. And as I said, the initial condition to create such a counterexample, we can even drop that and replace it with 0, which also makes the second term of Kirchhoff's formula vanish. So, and what do we use now for this admittedly artificial, but still for the counterexample, for the initial condition F, we use basically this very counterexample of my hill, only we take the absolute value, the length of the given spatial argument. Okay, so remember, of solution function u has several spatial arguments, a vector, and we take the Euclidean length of that vector squared. So that's the first component squared plus second component squared, and so on. And this is a single real number which we can then plug into this counterexample function of my hill. Only receives a single real number and returns a real value, and that is going to be our initial condition F. And then we see what comes out of Kirchhoff's formula in this case. Well, the first observation is that in this case, right, what is the value f of y? The value f of y is just h of the length of y. And now we're even going to restrict further. We're going to consider the case where x is equal to 0. So this is what you see here. What is u of t comma 0, where 0 now means the 0 vector in x. So in this case, here we take the average of the initial condition f on the sphere around 0, right? X is 0, the origin of radius t. And since the function f, by the way we construct it, depends only on the length of the argument, therefore the average value of that function is just the function value, right? So that this here simplifies to this expression, and there is a factor of t because, so this is the 3D case, the surface of a sphere scales quadratically with t, but we only divide by 1t, so there's another t remaining. So yes, I lied here. This is not the average. For the average, we would need to divide by t squared. Instead, we divide only by 1t, and that 1t is remaining. And here's t squared, because this is how we defined our initial condition. So put differently, for this special kind of initial condition, which is does not depend on the direction, only on the magnitude of the argument. For this case, Kirchhoff's formula simplifies drastically to become this expression, and here the time derivative becomes an ordinary derivative, and we can calculate that using the usual rules of differentiation, right? So this is a product rule and the composition rule, and well, you name it, so it amounts to this expression. Okay, you can calculate it by yourself. And now let's look at this expression and see what happens, for instance, when t is 1. And remember, the way that Myhill constructed his counterexample was such that it is actually uncomputable. Derivative is uncomputable at argument 1. So what happens if we here plug in t equals 1? Then we have h prime of 1. This is an uncomputable real number times 2, right? Multiplying an uncomputable real number with 2 is still an uncomputable real number, plus adding h of 1, which is a computable number, right? This is without derivative. So solving that for h prime of 1 means h prime of 1 is this expression minus this expression divided by 2, and that by construction is an uncomputable real number, which requires that also this number must have been uncomputable, which is exactly what we wanted to say. So this is an artificial computable initial condition to the wave equation, so that at time t equals 1, in the origin, the value of the solution is an uncomputable value. And this has been bugging people for quite some time from the perspective of the Church-Turing hypothesis, which says that basically any computable, any process in nature should be computable, right? Should be able to simulate up to any desired precision on a digital computer. But apparently the wave equation violates this Church-Turing hypothesis. The wave equation with a computable, artificial but computable initial condition results in an uncomputable solution even at the origin at time t. So can we use that to construct a more powerful computer, a wave computer, where we kind of instead of preparing a Turing machine tape and then starting the Turing machine's computation, which cannot solve the halting problem, how about we take a wave computer, prepare an initial shape of the initial wave according to this artificial but computable function, and then let the wave evolve on some perfect C, let's say, and then measure the amplitude after 1 second at time t equals 1 in the origin, and that would allow us to recover the solution to the halting problem, because that's how we constructed, how Myhill constructed this example. But this is physically infeasible, and this leaves maybe a little bit the realm of this lecture, but let me mention that, because what we can actually measure are not really the amplitudes of the waves, but only the average amplitudes over some small interval in the, or the energy, the L2 norm. So basically the reason why this violates the Church-Turing hypothesis is because we use the wrong norm on the space. Namely, we should not use the supremum norm on the continuous function, but we should use the local average norm, which is, for instance, the L1 or the L2 norm on the space. And thus, yeah, it was worthwhile an attempt, right? So science had almost found a way for solving the halting problem using a non-digital computer, using an analog computer, using the wave computer, but only almost. Then mathematicians jumped in and pointed out that we have been using the wrong norm all the time. Okay. So just a second. Right. Okay, this was our second counting example after the Myhill current example. And in the remaining 10 minutes of today's lecture, we're going to start preparing for the uncomputability of the root and of the argmin functional. This is an important result due to Ernst Becker. And again, we start our construction. So our goal is to construct a function, a computable function, actually even a smooth C infinity function, which classically we know attains its minimum, right? On C infinity function on the unit interval must attain its minimum, right? Even every continuous function. But we're going to construct the function in such a way that it does attain its minimum actually on many points of the unit interval, but on no computable points. It's a very sophisticated construction. And actually, we're going to construct the function also in such a way that its minimum value is 0, so that this also answers the question about computing roots and computing argmin, both negatively for a computable and even a smooth function. So whenever you see some library claiming to be able to compute the root of a given continuous, computable, or even smooth function, or claiming to be able to compute the argmin of such a function, be suspicious. It is not possible in general, and smoothness does not help. And this is, again, something that I find numerical scientists to be generally very unaware of, that some things are fundamentally not computable. And there's no point in trying to find algorithms for this problem, right? This is like trying to find a solution to the Haldane problem. That's a waste of effort. Okay. So, and again, our construction of this admittedly artificial counterexample starts with a positive case, namely by considering this head function again, which is again one Lipschitz function carefully scaled, so and shifted. So here the center is Cm, which is going to be a dyadic rational number, and its width and height is Rm, which is going to be another dyadic rational. And here you can see an explicit expression for that head function. So it vanishes outside, and it is this piecewise linear function, which can be expressed using the absolute value function like this. And again, we're going to superimpose several of these scaled and shifted functions in a very sophisticated way to arrive at the counterexample. So first we're going to prove a lemma. So we're going to consider two computable sequence of dyadic rationals in the sense that you've already discussed before, centers and radii. And the statement says there exists a function whose set of zeros, right, inverse image of 0, are precisely all arguments in the unit interval, right? It's a function in the unit interval that do not belong to any of these open intervals from here to here, right? So you see this head function is non-zero precisely outside of this. And if we take another such interval, and we take the union of all these intervals, then the resulting function will be strictly positive on the union of these intervals, and it will be 0 precisely outside of the union. That's the statement. But the important thing is that this function will be a computable function. Okay, so we start with such a computable sequence of intervals, if you like, and arrive at a computable function. And I call this a computable Urison lemma because Urison lemma, which you may know from set theoretic topology, says that there exists a function to every closed set. There exists a function which is 0 precisely on that closed set and positive outside of that closed set. And this is exactly what we have here. This is a closed set, and this is also a closed set, and outside of that closed set the function is positive, and inside the closed set it is 0. So I like to call this a computable version of this Urison lemma in the, okay, admittedly in the restricted case of topological space of the real unit interval. Good, and let's prove that. The proof is very simple. We just take the sum over all these heads again. Okay, we already had that in the previous construction, but the difference now here is that these heads are now allowed to overlap, right? In the previous construction of Myhill, when we had these heads, they had disjoint supports, right? But here, there's no hypothesis about these supports being disjoint, and in general, they don't need to be disjoint actually. So why is this function still computable? Why is this function even well defined, right? We have this infinite sum here, and so it may easily diverge, right? But the trick is here we're scaling, as we see here, we're scaling down the height of these heads artificially or in addition to their original height. The original height is Rm, like the radius, but we scale down the Rm even further, so that this this should be computable sequences in 0-1 interval. Let me add that. So in this way, this sum always converges, right? It's an exponential series, and it's easy to compute, namely to approximate up to error 2 to the minus n. We only need to look at the first n terms in this infinite sum, and that's easy to compute. So for computational purposes, everything becomes finite. Okay, so that's the first part of the statement. We've constructed a computable function that vanishes outside of these open intervals. But now the second part is actually a strengthening. Namely, we want to, in the end, we want to have a smooth function, a C infinity function. And to this end, we're going to replace these heads with this modifier that we talked about previously. So we want to construct not just a continuous function, this is continuous, right? But we want to construct an C infinity function to get this. And again, we use this modifier that we talked about before, which are computable. And we replace all these pulses, these heads, with these modifiers, and then repeat the same construction as previously with this modifier to arrive at a computable C infinity function with this property. Good, so this is the first step towards the construction of a counterexample of a computable, actually C infinity function with uncomputable root and with uncomputable argmin. Let's now, and this is going to be the last part, a step in today's lecture, turn that into such a computable function. Namely, we're going to prove that such sequences exist. We're going to construct such a sequence CM centers in ready RM, computable sequence, so that all these intervals contain all computable real numbers in the unit interval. And now observe that then by the very construction, this computable function, well, it must have roots, it must attain its minimum 0 in some points, but necessarily not in any computable point because we've constructed these intervals such that they contain and cover all computable points. All computable points are put into these intervals where the function does not have a root, does not attain its minimum, so that all the points where it does attain its minimum, and it necessarily does by calculus, must be necessarily uncomputable arguments, right? Does it make sense? So this is a very sophisticated and again, admittedly, artificial construction, which takes away all the computable, countably many computable real numbers and makes the function positive in all these computable real numbers, so that it has roots. It attains its minimum only on the remaining real numbers, which must therefore be all uncomputable one. And to make this non-trivial, as I said, I keep claiming that this function actually attains its minimum, which must be 0. And we're going to, this statement says actually the number of points where it attains its minimum, the set of roots of this function, right? The minimum is the root 0, has measure greater than 1/2, namely the set which covers all the computable real numbers where the function does not attain its minimum must have measure less than 1/2, but the unit interval has measure 1. So the remaining numbers, which covers all, includes all its roots, must have measure greater than 1/2. So, and we're going to prove that lemma on the next slide on Thursday. So last statement for today is the observation, the corollary, by combining the two lemmas, that there exists a computable function and actually even a C infinity function, such that the set of roots which is also the set of points where it attains its minimum, has measure greater than 1/2, but contains no computable real numbers, because all computable real numbers have been put into these small open intervals where the function is actually positive and therefore not a root. Okay, so that's all for today. To summarize, we've started talking about advanced aspects and in particular about sophisticated counterexamples of uncomputability involving computable functions. And our first counterexample was Myhill's statement theorem construction of a continuously differentiable and computable function whose derivative is not differentiable, actually is not differentiable at 1. Our second was building on that, the Purell-Richards construction of an initial condition to the wave equation, which is computable, but the solution of the wave equation is not computable at time 1 in the origin at 0. And currently we're on a way to prove Specker's theorem, this very statement. There exists a computable and even a smooth function such that the set of roots, the set of points where the function attains its minimum, is large. It has positive measure, but it contains no computable real number. And this is also what is sometimes called a singular covering. One can compute the countable set of computable real numbers. One can cover that classically by arbitrarily small intervals, right? But here it is covered in a computable way by such small intervals. And this is exactly what we're going to prove. This is a statement of this lemma, and this is deferred to our next lecture.